Hi, I'm Sarthak Jain, and this is a demo video for Lab-5 for EE533 under Professor Young Cho. This video is on behalf of me, Sarthak Jain, and my teammates Justin Santos and Archit Sethi. Now, Lab-5 wanted us to explore and expand more on Lab-4, where we created the bit files for our reference router. And in this time around, we were supposed to get the reference router, the ILA, as well as the IDS system incorporated all together and see if our bandwidth gets compromised and our registers are able to communicate between the CPU and the FPGA. The first thing I'm going to do is to explain how we created an ILA, because that was one of the most important parts of the lab. And following which, I'll go into why we created that ILA, how we incorporated it into our design, where we put it, how it works. Then following which, I'll explain the software-hardware interface and rest of the files that were created as a part of the simulation and the synthesis. The first thing I'm going to do is explain the diagram of the ILA. If you see on the screen, we'll see that this is the block diagram that we conceived for the ILA before coding it into our HDL, which is Verilog. We have a memory that will store all the data coming in and going out of it. We have a write pointer counter and a read controller, which will essentially control when and how my data goes into my memory. The stop signal at the bottom controls when my trigger at the input comes in, and then how many counts of data we need after my trigger comes in. So for example, I'll explain on the basis of a timeline. Suppose this is the timeline that we have, and at the beginning of the timeline we have the reset, and after a little while we have a signal called primed. This primed signal will basically tell my CPU that I am ready to get my input trigger. My FIFO is ready with some values and it's not garbage. We are ready to get the trigger. A little bit of a time later, we'll see that after a little bit of time has passed, we'll see some of the triggers coming in. Suppose this is the trigger that we need for our signal. And at this point onwards, we'll see the data going into the memory like so. Some data before the trigger and some data after the trigger will be sent into this memory. The reason we want data like this is because we need a reference point. Before the trigger is where the correct data is, and after the trigger is where my potentially incorrect data or the data of interest is. And in between, I have a circular FIFO. So this memory essentially is a circular FIFO that keeps on filling, and filling, and the write and the read pointers keep incrementing based on how many data points we need. Following which, the challenges were to actually figure out whether to create an FSM for this design or not. And for this particular design, we did not go for an FSM. I'll show the ILA top. For this, I created a read-write controller that essentially says whether we want the data to be stopped or not, which pertains to this counter here that says how many counts after the trigger we need the data to stop. So the write controller, the read controller, the stop counter, which essentially takes in a trigger, sends out a primed signal to the CPU, and the memory. After that, we have the generic registers, which essentially is a memory map. What this generic registers will do is create a map between my CPU and my FPGA of sorts. Whatever goes into the software registers will be read by my FPGA and be written to from my CPU. Whereas in the hardware registers, this will be written to by my FPGA and written by my CPU. So we are essentially having setting up a communication between the CPU and the FPGA using these generic registers. This count and these ILA shift registers are essentially storing the data and sending it out towards my CPU using the hardware registers. The next challenge of this particular lab was to figure out where to add my ILA. And before that, I'm going to explain how my circuit actually is behaving, or how my reference router is behaving. For that, I go to this particular diagram on the screen. As we see that we have certain input queues, which will get the data in, get all these data into particular queues based on the CPU, get arbitrated into my, using the arbitration method, we'll go into the output port lookup. And the output of the output port lookup sends the data into my IDS, which essentially contains my 7-byte pattern matcher, as we discussed in lab number 3. And the output of this IDS sends the data out to output queues. Now, this is where my drop FIFO packet is as well, which means if my input pattern matches the pattern that's coming in from this particular port, we'll drop that particular packet and let the rest go. Now, whether or not the packet is dropped or not, we send the data into the output queues, which is devoid of the malicious pattern, which will be dropped by this particular module here. The output queues will then send the data to the output queues, which will then be read by either the FPGA or the CPU. Now, one of the challenges using the iPerf scripts was to figure out whether my data is actually coming in from the CPU and going out towards my FPGA or not. The first thing we did was to create an ILA somewhere around here, which is between the input arbiter and my output port lookup. So essentially, we created some registers where the input data registers would feed into my ILA to see if my data is coming into my arbiter, and then from the output port lookup to see whether my data is actually going out from my output port lookup. Now, this essentially told us that the data flow is coming in from the arbiter and actually going out from the output port lookup, and there seems to be no trouble there. We were able to ping most of our nodes using the servers, using the scripts that we had, the iPerf scripts that we had as explained in lab 4, and then we needed to figure out the next part, which is whether my data coming in from the output port is actually going through my IDS and outwards towards the output queues. The next part was to create a bit file that had an ILA instantiated somewhere around this part between the output port lookup and the IDS. And again, the data that is incoming towards the output port lookup is sent into my ILA, and the output registers are actually sent towards my IDS outputs. Now, this basically told me that my registers are kind of working correctly, because I was able to see the data coming in from here through my IDS and outputs from here, which again told me that there seems to be no problem in the IDS module instantiation as well. The last portion was, as again described before, was to create an ILA between the IDS and the output ports, and as before, I was able to check whether my data is flowing correctly through these modules or not as well. Now, following this, we were able to debug quite a lot of errors into our code, for quite a lot of signal problems, data not coming in, coming out, and we were essentially finally able to get the data flowing right from the input queues towards my output queues. The demo of which will be shown by my teammate Justin. Finally, the hardware-software interface that we created for these registers, we had to also instantiate into our user data path. So let me go to the GitHub folder and show you what I mean. Now, in this folder, we'll have the input arbiter ILA, which means that we'll have the ILA between the queues, input queues, and the input arbiter. We'll go into the source, the ILA top. Oh, let me go into the user data path first. As we see in this particular code, we have this ILA top in control. These are the ILA signals that will essentially be input to my arbiter and output to my lookup ports. And let me pick up one of the signals and search. Essentially, if you see that this is my output LUT data in, oops, this is the input to my ILA, which essentially is the data coming from my input arbiter. So we are sending the data from the input arbiter into our ILA to see whether the data actually flows correctly or not. These are the register interfaces we have to connect between the output lookup and the arbiter. Essentially, after we added the registers into our ILA and instantiating it into our user data path and using a make command into our synthesis folder, I'm going to show you how the registers were created in our interface. So the first thing I'll show you is that apart from creating those software hardware registers, so for example, these primed, triggered, and ILA part 1, part 2, max count, and trigger I, we had to create an then XML file that actually helped my software map my registers into the hardware using synthesis. So if you see, we have the ILA top here, we have the registers declared, that were essentially my generic hardwares, which were essentially hardware registers. Now this 128 byte is a block size, which essentially is the number of registers that we have multiplied by 4. And this is the block size we'll need. For safety purposes, we'll take a little bigger than the number of registers that we have. So for example, if we have 16 registers, we'll multiply that by 4, and we'll have that particular block size here. So these are my this is my ILA that we created for my this is the XML that we created for my ILA, and the registers.v after the make will show you the instantiation of these registers. So as we see, in the registers.v, we have the hardware macros defined for those particular registers, which is pattern high, pattern low, command matches, which are from my 7-byte matchers, and the ILA top, upper, and lower, which we defined in the ILA. Now this was generated automatically after we ran the make command, and courtesy the XML that the ILA top and the underscore top.xml that we created. Secondly, we also created the make file also created and reg defines ILA IDS, which mapped the addresses between my software and my hardware, which essentially means that most of these addresses were the mappings between the CPU and the FPGA. Whatever values my CPU would write to these addresses, which would then be read by my FPGA and vice versa. So if you see here, this is my IDS file registers mapped to certain addresses, and in continuation contiguous blocks, we'll see that my ILA registers have been defined as well to certain addresses. So essentially 120C, then this is a contiguous block, so therefore we'll have 1280, 1284, 1288, and so on and so forth for the number of registers. I'll very quickly show other parts of my ILA as well. So this is the monitor underscore IDS to OPL, which is essentially, as we showed in the diagram, the ILA between my output port lookup and my IDS. Again, in my user data path, I'll go into my ILA. And if you see, this input in ready is basically to figure out whether my ready signal was becoming 1 or not, which essentially means that my ILA was sending a ready acknowledgement uh, to my output port lookup to accept data. So if we see that this IDS signal, this in ready, actually generates this IDS in ready, which is an output from this port. This in underscore ready is a receiving signal. This is an output from the IDS. Then this goes into my ILA to monitor whether the two paths are actually correctly working or not. And again, these are the register interfaces we need to connect between the two modules. The rest of the XML was same. That we created the XML that generated my registers.v and again some of the address mapping in the C directory. And finally, we have the ILA between the output port and the IDS. As we see here, we'll see that OQ in ready is the data from my IDS to my output queues. So as you see, this output ready signal is essentially the data that we are looking at. This goes into my IDS from my output queues, this guy here, which essentially tells that that my IDS is actually ready to send out data and my output queues is ready to accept data from my IDS. Now, in practice, will be shown by Justin how we see those particular signals. And again, as before, we were able to generate those registers from using the make file. And the rest of the demo will be explained to by Justin. Thank you.
So here I'll go through their code, and this is our GitHub repo, and we have multiple instances of different projects, and I'll go through the out ready of ILA, which is essentially monitoring the output of the output queue that is triggered and sent to the input of the IDS. And so first I'll go through the include, and we have the project XML, and this project XML will instantiate and call ILA top, which is our ILA design, as well as the IDS XML. Additionally, we have our ILA top XML. And so opening that up, we can see that there are multiple data registers. And so we have 64-bit inputs and within our ILA, and then we distribute that into two 32-bit registers. And so for instance, we have a 64-bit input for data in 0, and that will be spread into two registers. We have ILA upper 0 and ILA lower 0. And ILA upper 0 is the 32 bits of the data input, and then ILA lower is the lower 32 bits of the data input. And we create 8 of these registers, so registers 7 through 0, which in total will be 16 registers, because each register is 32 bits for each 64-bit data input. And so now, having looked at the include, we will look at our library folder. So after having synthesized and implemented and generating the bit stream, we get the reg defines, which will show all of our addresses for the registers. So if I look up ILA, we'll be able to see the starting point of our ILA for the top. And here are the addresses that we'll use for our IDS reg. So here are the 16 registers that we use for the ILA. And here are the registers that we will use for the IDS registers, namely for the pattern high, low, IDS command, and the matches counter. Additionally, I'll show the ILA being instantiated within the user data path, showing what we are figuring and monitoring. And so here, if we scroll down, you'll see the ILA instantiated after the IDS, and the ILA top will have its data input. So this is the signal that we're monitoring, and the output queue in ready is what we are going to monitor, which is the output of the output queue, which will be shown right here. And this output of the output queue will also be the input to our IDS, as shown here. So now I'll upload one of the bit files that we have. As you can see, we have multiple bit files, and just to point out, this data bit file is the bit file that shows the output data of the ILA. We have another bit file here that shows the output of the output lookup to the ILA, or to the IDS in this case. And we also have another one which is the out ready of the output lookup port that goes to the input of the IDS. So to show that we get data, I'll put the data bit. And so first we're able to successfully upload and download this bit file. And so we're also able to read all our registers. So these are our IDS registers, as well as we can use a command that we made, ILA_regs, to show all of our ILA registers. And our initialization value is BADA-BDAB. And since it's not showing dead beef, we can be sure that we're reading from the correct address. So now that we can see that our ILA registers are readable, as well as our IDS registers, we now set the IDS reg pattern to something like ABCDEFG. And we also edited our IDS reg to show that depending on the pattern, we're able to output if we're setting a mask bit for each byte. And in this case we are, and that's shown because we have chars for all of the bytes, as shown by the most significant 8 bits. So since it's 7F, that means for the hardware register A, we have all the mask bits set to 1, meaning we have to meet exactly all the byte patterns. And after having set the pattern, we should be able to ping nodes. And from this, we can see that we're able to ping the node itself, but also we're able to ping other nodes, ping N2, ping N3, as well as ping N0. So now that we're able to show that we ping, we can read the data coming into the IDS because our ILA is monitoring it. And so here we can see that data is being sent to the ILA and to the IDS as well. Additionally, we can check our IDS registers, and we can see that we have the pattern here, as well as not having found any matches. And so on this next section, we will showcase that we're able to find the matches and still ping. So now I'll change the pattern to DEFGHIJ, and we can see that we're setting mask bits for all the bytes, and we can confirm that by the 7F, indicating that we have all chars and no don't chars. And we can also see that we have no matches yet, and so we'll set up an iPerf server and client, and the client will send a bad packet, and we should see that the matches increments. So we'll set up an iPerf server here, and we have a bad packet that will be sent, as can be seen by the DEFGHI. And sending that packet, we should see that we connect, but there's no data going through, and that can be seen because the connection has not been terminated, and we can see that all regs we have matches that have incremented, and so we have caught the matches. So now I'll show that we can send a good packet and a bad packet at the same time, and so I reset the counter, and now I'll start the server, and here we have a good payload, and this is what the good payload looks like, and we have none of our pattern here. And so now we'll send that good payload to the iPerf server, and you can see that it was able to go through properly, and we can confirm that we're able to let that go without incrementing any match. And then afterwards we'll send the bad payload, and we can see that we connect to the server, but we're also unable to get the data through, as can be seen by the matches here.